at POPL 2021. It is my pleasure to introduce James Benjamin Worrell, who goes by Ben Worrell in the community. Ben is English, if you couldn't tell from the accent when he starts talking. Studied mathematics at Oxford and did his PhD in computer science there on coalgebras. After 5 years in the US, he went back to Oxford, where he is a full professor now. He received the highly prestigious EPSRC Established Career Fellowship in 2016 and was a recipient of the 2020 Saloma Prize for Outstanding Contributions to Theoretical Computer Science, jointly with Joel Wagner. Ben has been an invited speaker at many conferences before, including most recently at LIX 2019. Completely by coincidence, he has become a first-time POPL author this year. For those of you who understand cricket, Ben is related to Sir Frank Worrell, who apparently was a cricket superstar. His work in the past few years has been in the area of algorithmic analysis of dynamical systems using tools from number theory and algebraic geometry, and he will share the fruits of this particular labor with us today. For those of you who want to ask questions, Ben graciously has agreed to be interrupted with questions. You can post your questions on the chat in Zoom. I will exercise a little bit of judgment in when to interrupt him, and we'll take hopefully most of the questions at the end when he's done. Over to you, Ben.
Okay, thank you very much for the introduction, Azada. Can you hear me okay?
Yes.
Okay, so, well, thank you also for the opportunity to give a talk at POPL. So as you mentioned, I had my first POPL paper in this conference. So I'm very grateful to be invited as a speaker. Okay, so the title of my talk is Loop, Termination and Dynamical Systems. So what is the talk about? So in a word, the subject of the talk is does this program terminate? So here is a linear constraint loop. So in the next few slides, I'm going to explain a little bit the context of this problem and exactly make precise what this loop is and what is meant by termination. So to start, I'm going to consider the following article, which appeared in the Communications of the ACM in 2011 by Byron Cook, Andreas Podelsky, and Andrei Rybelchenko. And the message of this article is that the article is about proving program termination, and the message of the article is, in contrast to popular belief, proving termination is not always impossible. So in particular, within the article, the authors say that termination tools can automatically prove or disprove termination of many famous complex examples, such as Ackermann's function or McCarthy's 91 function, as well as moderately sized industrial examples. So one of the papers that forms the basis for that survey article was a paper by Podelsky and Rybelchenko that appeared in VM-Chi, and which is about a complete method for the synthesis of linear ranking functions. So in the abstract of this paper, they say that we present an automated method for proving the termination of an unnested program loop by synthesizing linear ranking functions. And the method is used as a subroutine for program termination and other liveness properties of more general programs via transition invariants. So at the core of this, there was, the core of this work of Podelsky and Rybelchenko, there was a complete method for synthesizing linear and lexicographic linear ranking functions for linear constraint loops of this form. So what is a linear constraint loop? So it's a loop where you have some variables x, and the loop guard is a conjunction of linear inequalities. So here it's written as bx greater than or equal to b. And the body of the loop is not a system of assignments, and there's no control flow. The body of the loop is simply a conjunction of linear inequalities between values x when you enter the body and values x prime, the values of the variables upon exiting the body. So it's a constraint rather than an imperative program. So a conjunction of inequalities. And for such a loop to terminate means that for all initial values of the variable, when you enter the loop, you shouldn't run forever. So but you're talking about all possible initial values. It's a universal problem. And what they offered in the paper is a methodology for this. And the methodology was, well, given the program, to prove termination, you would synthesize a ranking function, in particular of a certain kind, and the method was complete. So if a ranking function exists of the specific kind, then the method would find the ranking function. But note that notwithstanding this being complete, this does not necessarily solve the decision problem of the decision problem that asks, does this loop terminate? And we'll go back to that point in a second. But okay, but there was this method of finding ranking functions for these loops. Now I should say, of course, no one's ever going to write a program like this. There's no control flow, but this is an abstraction. And one of the contributions of the Podolsky-Rybulchenko paper was to take a real program and reduce the termination of a real program to termination of abstractions like this through this method of transition invariance. So it should be said that automatic synthesis of linear ranking functions has a history before the Podolsky and Rybulchenko paper. So for instance, an early reference is this paper by Sohn and Van Gelder on termination detection in logic programs using argument sizes. So in the abstract for this, they say the prospects for automatic termination detection of logic programs appear promising, in contrast to the bleak picture for procedural languages. So a very different view to the CACM paper. We describe a method of finding a non-negative linear combination of bound arguments that, if it is found, is guaranteed to decrease during top-down execution of the recursive rules. In other words, they're synthesizing ranking functions. And in fact, as was pointed out in this 2012 paper, and you look at the automatic synthesis of linear ranking functions, essentially Sohn and Van Gelder and Podolsky and Rybulchenko were kind of doing the same thing. So they say that in this paper, we present two algorithms, one based on work of Sohn and Van Gelder, the other due to Podolsky and Rybulchenko, and we show that the two algorithms are synthesizing a linear ranking function under exactly the same conditions. So the difference is one's working in the procedural setting, one in the setting of logic programming, and they're using different abstractions to boil down termination into this termination problem for linear constraint loops. But nevertheless, what they do is they solve termination for linear constraint loops by synthesizing linear ranking functions. But as I've said, that the method of synthesizing linear ranking functions and lexicographic linear ranking functions does not solve the, and is actually known not to solve the termination problem, the decision problem of termination. So the papers give examples of loops that terminate, but yet have no linear or lexicographic linear ranking function. And this problem as a decision problem was highlighted by Ben Amram, Ghanem, and Masood in their paper on the termination of integer linear loops. So they said, we feel that the most intriguing problem, that is of the problems that they discussed, is whether the termination of a single linear constraint loop is decidable when the coefficients are rational or integer numbers and the variables range over the integers. So again, just to be very concrete, the question is, given such a loop, will it terminate for every possible initial value of the loop variables as they range over integers? So this is the problem that I'd like to kind of base the talk around, and well, we'll see how far we can get. So in approaching this problem, let's do the sensible thing, and we'll follow the advice of Polya and try and start with an easier case. So this is George Polya, and he has this very famous advice, which you probably tell to all your first-year graduate students. If there's a hard problem you can't solve, there's an easier problem that you can solve, find it. So in our case, we don't have to look very hard because already in the literature, the easier problem has been identified. And this is the problem of termination of deterministic linear loops. So these are special cases of linear constraint loops where you still have a conjunction of inequalities as the guard, but the loop body, rather than being linear constraints between x and x prime, is an assignment. So an assignment X gets Bx plus C. So B here is a matrix, C is a constant vector, so it's an affine assignment. So again, I'm not saying that anyone's ever going to write a program like this. I'm just saying this is, through this process of abstraction, when one gets a linear constraint loop, this is the simple case. And this, it's very natural to think of this as a dynamical system. And the question is, well, does this terminate for all values of the program variables? So to be very precise, the termination problem is as follows. The instance is the syntax of the loop, the matrices A and B and the vectors B and C. Let's say they have integer entries. And the termination problem is parameterized by the type of the variables, the program variables. So let's say the program variables range over R. So R could be the integers, R could be the rationals, R could be the reals. And the question is, does the loop terminate for all initial values in R? So the problem was considered in 2004 by Tiwari in a CAV paper. And there he showed that the problem is decidable if the variables range over the reals. And he conjectured that the problem is decidable when the variables range over the rationals and integers. And the conjecture over the rationals was confirmed by Braverman in a CAV paper. So actually, I think there's a typo here. I think that was 2006, but anyway. So Braverman showed that the termination problem over the rationals is decidable. But he left open the problem over the integers. So at this point, before going any further, I want to just explain why, I'm making a distinction between whether the termination problem is over the reals or the rationals. Why does this make any difference? So here's an example that's taken from Braverman's paper that shows why the type of the variables affects whether the loop is terminating. So here's a loop that's going to be terminating over Q, but not over the reals. So there are two program variables, X and Y. And as you can see, the loop body is this simple linear assignment represented in matricial form. So we can understand this geometrically. That's the best way to think of this. So the values of the loop variables are points on the plane, and the values that satisfy the loop guard are the values in this pink region here on the plane. So the question is, well, does the loop terminate? So we can isolate kind of three subdomains of the pink region. So on the blue arrow, what happens to a point on the blue arrow when we apply the transition matrix of the program? So in fact, the transition matrix is going to take a point on the blue arrow and is going to move that point along the blue arrow. It's going to scale the point by a positive number. So in linear algebra terms, this blue arrow is an eigenvector of the matrix with a positive eigenvalue. So in particular, any point on the blue arrow, if I start there, I'm going to be non-terminating because I'm just going to move along the blue arrow and I'm going to stay in the pink region. I'll be non-terminating. If I start on the red arrow, so the red arrow is another eigenvector of the matrix, but this time with a negative eigenvalue. So if I start on the red arrow and I apply the transition matrix, I'm going to flip over and I'm going to scale myself by a negative number and I'm going to be terminating in one step. So these points are immediately terminating. So what happens for the rest of the points? So the points that are neither on the blue and red arrow. Well, what happens there is when you apply the matrix, the transition matrix, if you don't immediately terminate, the effect of the matrix is to move you closer and closer and closer to the red arrow. So to decrease your angle with the red arrow. So eventually, when you become aligned with the red arrow, you're going to behave as if you were on the red arrow and you terminate. So the bottom line is as follows. All the initial values you could start this loop with are going to be terminating apart from the points on the blue arrow. So the loop is non-terminating over R, because to be terminating over R means you terminate for all real values of the variables, and yet these points on the blue arrow are non-terminating. However, it is terminating over Q because, crucially, this blue arrow has no rational points. It has an irrational slope, and there are no rational points on the blue arrow. So for all rational values, you are terminating. Okay, so there's a distinction between termination over the reals and rationals, and Braverman showed decidability over the rationals. But he left open the problem over the integers, but he had this speculation at the conclusion of his paper, and he said, it appears that to decide termination over the integers, it is necessary to be able to tell, given a point, whether the program terminates on x0 or not. So which is to say we can make a useful distinction between two decision problems. The termination problem as we've been describing it up to now, and the so-called initialized termination problem, which I'm going to describe now. So the syntax here is not just the loop, but the loop with an initialization. And so the instance is the loop and the initial value, x0. And the question is, does the loop terminate when started on this initial value? And so clearly these problems are very closely related, but in fact they are quite different as well, as we'll see. Okay, so at this stage, I'd like to make a slight shift and kind of move to a slightly more abstract setting. So we're looking at this termination problem for initialized linear loops. Now, this can be understood in terms of the notion of a linear recurrent sequence. And this actually is this reformulation kind of generates quite a bit of insight. So what is a linear recurrent sequence? So it's a sequence of numbers. Well, let me start off by saying, well, the classic example that everyone knows is the Fibonacci sequence. So a linear recurrent sequence is a sequence of numbers that satisfies a linear recurrence. And that means that the nth term in the sequence is a linear combination of the preceding k terms. So this is a recurrence of order k. So here un is a linear combination of un minus 1 up to un minus k. So in the Fibonacci numbers, un is the sum of the two preceding terms. Now, the crucial link here with these linear loops is if I have one of these deterministic linear loops, and I look at the sequence of values assumed by a variable as I unfold the loop and I apply the transition function, this satisfies this sequence of numbers satisfies a linear recurrence. This is, I'm not going to explain why, but this is just standard linear algebra. So, so here is the kind of canonical linear recurrence sequence of Fibonacci numbers, and here they are displayed on the chimney of a power station in the Finnish city of Turku. And this is particularly appropriate given that a lot of the study of linear recurrence sequences from the point of view of computer science and automata theory has been carried out in Turku by the school of Salama. Okay, so these are linear recurrences, and we're trying to link these to loop termination, termination of these initialized linear loops. And we can isolate a particular decision problem for linear recurrences, which corresponds to the termination problem for these initialized linear loops. This is the positivity problem. So an instance of this problem is a linear recurrent sequence. So this can be finitely represented by a recurrence and the initial values of the sequence. So this has a finite representation. And the question is it the case that for all n, un is greater or equal to 0? So the link with termination of these initialized linear loops is, well, you have a guard, and the loop is going to be non-terminating if the guard always stays positive on every iteration of the loop. Okay, so there are some slight technicalities here, because our guard in the case of the linear constraint loop was a conjunction of linear inequalities, and we only have a single linear inequality here. But both morally and technically, these programs are equivalent. And this is what I want to think about now, this positivity problem. So this problem was identified long before this work on termination of linear loops. So this problem goes back at least as far as the 1970s. And in particular, it is described in this textbook, this very nice textbook of Arto Salama and Matti Soitola, automata theoretic aspects of formal power series. So it's also described along with other problems on recurrent sequences, such as Skolom's problem, in this textbook, Cornerstones of Undecidability by Rosenberg and Salama. Okay, so this is the problem that we want to look at for now. So I think at this point it's worth having a recap, because I've talked about several problems and you may be losing the thread of what's connected with what. So as I said, well, my first slide was about this termination problem for linear constraint loops. But then following Polya's advice, we decided to consider a simpler case of these deterministic linear loops. And then we saw, well, termination of these is decidable over the reals by Tiwari, is known to be decidable over the rationals by Braverman, but we were looking at over the integers, where it's still open. And but then we followed the kind of suggestion of Braverman of considering the initialized problem, where we fix an initial value and see what we can find about that. And as I've said, well, this problem, it turns out, is a long-standing problem, this positivity problem for linear recurrences. So we're going to think for a while about this positivity problem, but afterwards we're going to pop back up and say what this means for our original problem of loop termination. Okay, so well, how are we going to solve the positivity problem for linear recurrences? So we want to make sure that we're approaching the problem in the right way and we have the right tools. So here's a problem. Here's a paper that appeared 2 years ago in POPL, closed forms for numerical loops, and it was on a very similar subject to what I'm talking about now. And in the abstract of this paper, the authors say, it is well known that a closed form representation of the behavior of a linear dynamical system can always be expressed using algebraic numbers. But this approach can create formulas that present an obstacle for automatic reasoning tools. So the key point here is that, okay, we're trying to analyze the positivity of a given linear recurrent sequence. And a major point in our favor is that this has an explicit closed form representation. So in the case of linear recurrent sequences, this is what it looks like. So UN is a linear recurrent sequence. So someone's given me a recurrence and the initial values of UN. And what I can do effectively is compute the following closed form representation. So this is that UN is the sum from I equals 1 to k of some terms. And what are these terms? Well, these terms are a mix of polynomials. So pi of n is some fixed polynomial, and some exponential expressions, lambda I to the n. So lambda I is a fixed number. And in fact, what these numbers lambda I are they are roots of a polynomial that's associated to the recurrence, the so-called companion polynomial. So I won't go into details, but they're just numbers. And we have this closed form. Now, given this closed form, we can then try and solve the positivity problem from this. So we have a closed form. How hard can it be? So can we use some decision procedure or some automatic reasoning tools? So can we feed in this closed form into the automatic tools and it will spit out whether the sequence is positive or not? So, and what I'm getting at here is we want to use the right tools for the problem. So we don't want to bring a knife to the gunfight, kind of mathematically speaking. So to kind of find out or get some sense of, what is the right way to approach this problem, let me cook up a completely artificial example, which nevertheless contains kind of some important lessons. So here's a particular linear recurrent sequence, and I'm not specifying it by recurrence because now that we have our closed forms, in fact, I can specify it directly in terms of a closed form. So here's this sequence, and as I say, it's given in terms of its closed form. UN is 33/8, so some random number, plus lambda 1 to the n, plus the complex conjugate of lambda 1 to the n, plus 2 times lambda 2 to the n, plus 2 times the complex conjugate of lambda 2 to the n, where lambda 1 and lambda 2 are particular numbers. So lambda 1 is -3 plus 4i over 5, and lambda 2 is -7 plus 24i over 25. So please bear with me. This is a slightly technical slide, but I think there's a reason I'm bringing it is that there's, I think, some insight to be had here. So let me say in passing that these numbers, lambda 1 and lambda 2, are complex numbers, clearly, and they are algebraic, they're roots of a polynomial, and they are numbers of absolute value 1. So they're, they come from Pythagorean triples. So suppose I give you this very strange linear recurrent sequence, and I ask you, well, can you prove to me, I even tell you that this sequence is in fact positive, but can you prove to me that this sequence is positive? So you have at your disposal an arsenal of tools, and now what are you going to use? Now, at the first sight, it doesn't look so promising because it looks like a Diophantine problem. You've got this discrete variable n, and we want to check for all n, un is positive. And even worse, n is in the exponent position. So what decision procedure are we going to use? But in fact, this can be used, well, you can approach this problem, you can prove positivity using a continuous or a relaxation. You can use a decision procedure, let's say, for real algebraic geometry or decision procedure for real closed fields to prove positivity of this sequence. So in particular, you can actually calculate the infimum as n ranges over the natural numbers of un. Then it's going to turn out that this infimum is 0. So how do you calculate it? So the idea is well, like in optimization, relaxation. So you're going to replace the discrete variable with a continuous variable. So in this case, you're going to replace the discrete quantity lambda1 to the n with a complex variable z1. And you're going to replace lambda2 to the n with a complex variable z2. And then you're going to try and compute the infimum of 33 over 8 plus z1 conjugate plus 2 times z2 plus 2 times z2 conjugate. And you're going to have constraints on z1 and z2 reflecting the fact that they're meant to stand for lambda1 to the n and lambda2 to the n. So the constraints are that the absolute value is 1. And then you also have this multiplicative relation between z1 and z2, that z1 squared times z2 equals 1. And this reflects the same relation that holds between lambda1 and lambda2, and also between lambda1 to the n and lambda2 to the n. Okay, and I claim this equality holds. So this looks very suspicious because it seems like a very coarse approximation. Why should this equality hold? Well, I'm not going to say why, but it does. And in fact, this is not such a special case. This approach can be done in some generality. And this shows that you can handle the positivity of these linear recurrent sequences. Even though it looks like a problem in arithmetic, you can handle it using real optimization, so theory of real closed fields. However, this is not the complete story, because suppose I ask, well, let me change the sequence a bit and say, well, let me have a new sequence, Vn, which is un minus 1 over 2n. So again, it turns out this is a linear recurrent sequence. And I ask you, is this sequence Vn always positive? In other words, what I'm asking is, this sequence un, which we know has infimum 0 and is positive, is this sequence actually always, does this sequence un always dominate 1 over 2 to the n? And in fact, this problem cannot be approached using these kinds of continuous over approximations. It cannot be approached using kind of real algebraic geometry or decision problems for the reals, as far as I know. This problem is inherently Diophantine. It's inherently about arithmetic. It's inherently about number theory. So I want to just in a couple of slides to explain via some very simple examples, the kind of tools that are relevant for this problem, because these are the tools that are relevant for proving that a linear recurrent sequence is positive, and therefore they're the tools that are relevant for solving this initialized termination problem for linear loops. And in fact, these tools are going to be, at first glance, very far removed from the kind of milieu of program analysis. So let's consider the following problem. So I mean, just to explain what I'm doing, I'm not referring directly to these linear recurrent sequences, but I'm considering something that's very closely related, just so that you can see the relevant tools. So here's a problem in arithmetic. How small can the following expression get? So 3 to the x minus 7 to the y, where x and y are natural numbers. So the connection with the linear recurrent sequences here is that these are sums of powers, which is what the closed form expression for the linear recurrent sequence look like. Now, how small can this get? Well, clearly this expression couldn't be 0, because I could never have 3 to the x equal to 7 to the y. But maybe it could be 1 for some values of x and y. Maybe there are infinitely many values of x and y such that this are 1. Or maybe it's the case, for instance, that there are only finitely many values of x and y such that this is, say, less than 100. So how small could this be? Well, in fact, what holds is the following, is that remarkably, for all but finitely many values of x and y, this difference between 3 to the x and 7 to the y is essentially almost as large as the largest of the two terms. So more precisely, given any epsilon greater than 0, for all but finitely many x and y, 3 to the x minus 7 to the y, the absolute value is greater than m to the power 1 minus epsilon, where m is the maximum of the two values. So almost as big as the biggest value. So they don't cancel each other out. Okay, so I'm asserting that's the case. Now, how is this proved? So this is proved, so to prove this, you need seemingly non-trivial machinery. So a result that you can use to prove this is a result called Baker's theorem on linear forms and logarithms. So this was proven by a number theorist from Cambridge called Alan Baker. And this result was cited in his Fields medal. And what the theorem allows you to get in this case is effective bounds on x and y that, so for instance, you can say for x and y greater than, 1000, 3 to the x minus 7 to the y is always greater than this lower bound, m to the 1 minus epsilon. Okay, so these are the kind of tools that are relevant for proving lower bounds on linear recurrences. Now, let me just give you a slight generalization of this problem in arithmetic. Suppose I have now 3 terms, 3 to the x plus or minus 7 to the y plus or minus 13 to the z. And I ask exactly the same question. How? Oh. Sorry, can you still hear me?
Yes, all good.
Yeah, okay, good. Yeah, so I ask, how small can this quantity get? So this is exactly the same question as before, but I now have 3 terms. And you get a very similar answer to that we had before. So given epsilon greater than 0, for all but finitely many x and y, the sum of these 3 terms is more or less as big as the biggest of the 3 terms. So it's greater than m to the 1 minus epsilon, where m is the maximum of the 3 terms. So far it looks the same as with 2 terms, but there's a crucial difference. So the first difference is the kind of machinery that you need to prove this. So here, the proof of this bound comes from a result called the subspace theorem. And what this is a higher dimensional generalization of a resultant number theorem, Roth's theorem on Diophantine approximation. And again, this is a theorem due to Klaus Roth, again, a Fields Medal winning result. And what's different here is that these bounds are non-effective. So one can say that this inequality holds for all but finitely many x and y, but you can't place a bound on x and y by saying that, well, all the exceptional values of x and y, or I should say x, y, and z, are less than 1,000 or less than 1 million. You can't say this. You just don't know. Okay, so I hope this is not too far removed from what we were talking about, but you'll see a ghost of these facts when I state the main result that I want to talk about in terms of positivity, which is the following. The positivity problem is decidable for linear recurrent sequences of order at most 5 and for simple linear recurrences of order at most 9. So the order, if you remember, is the depth of the recurrence. So the way to understand this is when I reinterpret this result in terms of deterministic linear loops. So interpreted in terms of deterministic linear loops, what this says is this initialized termination problem where you're given the initial value and you're asked, does the loop terminate? This is decidable for deterministic linear loops with at most 4 variables and with at most 8 variables if the update matrix is diagonalizable. So unfortunately, you're not going to be able to solve any industrial scale examples using these kind of number theoretic techniques. Now, you might say, well, maybe you're barking up the wrong tree by using number theory. I mean, why not use linear ranking functions or some other approach? But in fact, what one can show is essentially is that these problems are inherently number theoretic, at least if you want to solve them in all cases, in as much as improving on these decidability results by kind of extending it to higher order linear recurrences or loops with more variables, this would entail breakthroughs in an area of number theory called Diophantine approximation. So, I mean, this is a very informal statement, so this is not a theorem, but there is a theorem in the paper above that corresponds to this statement. Okay, so where are we? Well, we've kind of figured out that this initialized termination problem for deterministic linear loops, well, it's solvable in low order, but essentially this is a really hard problem. But this is not actually the problem that we really wanted to solve at the beginning. So maybe this is a case of sour grapes, but I'm telling you, this is not the problem we wanted to solve. The problem we wanted to solve was this general termination problem over Z. So in order to kind of compare the problems, let's introduce some notation. So I have an initialized linear loop shown in the blue box. And let me define NT to be the set of non-terminating initial values. So these are the set of values, x0 and Rn, such that such that the loop is non-terminating when I run it starting on x0. So the problem of initialized termination asks, does this specific value live in the set NT? Whereas the general termination problem, as posed by Tiwari, asks, does this set NT contain an integer point? Is there an integer point that's non-terminating? So clearly this set NT, well, it's well defined as I've defined it above, but clearly we cannot hope to have an effective characterization of this set, because if we did, we'd be able to solve the initialized non-termination problem. But on the other hand, if we don't have an effective characterization of the set, how are we going to decide whether it contains an integer point? So how are we going to solve our problem? So it turns out that we have kind of an almost effective characterization of the set. And what this characterization stems from was the kind of techniques that I was talking about earlier when we considered the specific linear recurrence, and we considered this kind of continuous approximation using real algebraic geometry, theory of the reals. So what we have is the following. There exists a convex closed semi-algebraic loop invariant C. This set here, so semi-algebraic, it's given by a conjunction of polynomial inequalities. This can be effectively generated from the loop. This satisfies the following. It's almost equivalent to the non-terminating set. So the interior of C is included in the non-terminating set, is included in C. So the only differences are at the boundary of C. And these differences are essentially why the initialized problem is hard. So the hard instances of the initialized problem are on the boundary of C. And even better, this non-terminating set contains an integer point if and only if this set C that we can get our hands on contains an integer point. So this gives us a route to solve the termination problem. So we need to ask, does this set C, which we can compute, does this set contain an integer point? If not, then our loop is terminating. So, so the problem is, given a convex semi-algebraic set, can I decide whether it contains an integer point? Now, this maybe at first glance seems a little difficult, because isn't this Hilbert's 10th problem? Like Hilbert's 10th problem is essentially, does a semi-algebraic set contain an integer point? But crucially here, convexity makes all the difference in the world. So there's this very nice result of Kacyan and Porkolov, who show that it's decidable whether a convex semi-algebraic set contains an integer point. So in other words, Hilbert's 10th problem for convex sets is decidable. Okay, so with this in hand, we can decide the termination problem. So let me just skip over this and say, well, we have the following result. So termination of deterministic linear loops over Z is decidable. So this is a result from ICALP in 2019. Okay, so now you might be expecting, or you might be hoping, or you might be fearing that I'm going to go on and start talking about these constraint loops, because we were solving a special case of the constraint loop problem. But in fact, this is still open, so I don't know how to solve this, but this is a problem that that we're currently thinking about. And one other point I'd just like to reiterate here is these are asking termination over all initial values in Z. So as we said, these initial termination problems, these remain beyond reach. These look very hard, but this general termination problem for linear constraint loops over arbitrary initial integer values, this is not necessarily beyond reach. So in the last 10 minutes of the talk, I'd like to just go off in a slightly different direction. So let's go back to this CACM article, and the article, after talking about termination for linear loops, goes on to talk about nonlinear extensions. So to highlight the words in red, they say to improve the current power of termination provers, further developments in nonlinear reasoning are required. So in terms of this kind of foundational kind of mathematical setup that we're working on in this talk, what's the corresponding problem of termination of loops with nonlinear assignments? So in fact, there's a very canonical choice of approach here, which is to generalize beyond the notion of linear recurrences to the notion of a kind of nonlinear, well, of a more general notion of recurrence, which is the notion of a holonomic or p-recursive recurrence. So a sequence of real numbers is holonomic or p-recursive if it satisfies a linear recurrence with polynomial coefficients. So here's such a recurrence. So the coefficients p0 up to pk are some fixed polynomials. And again, we have the nth term of the sequence is a linear combination of the previous k terms with polynomial coefficients. So I'm not going to explicitly make the link here with loop termination, but as we're going to see, the positivity problem here is going to be this kind of mathematical formulation of loop termination for loops with nonlinear assignments. So what are some examples of these holonomic sequences? So here's one. So un equals n factorial. And the recurrence here is clear. Un is n times un minus 1. So these sequences occur very frequently in combinatorial settings. So let un be the set of n derangements, so the number of permutations of n letters that leave no letter fixed. So this, again, satisfies a holonomic recurrence. So further examples are the Fibonacci numbers. So they're a linear recurrence, so they certainly satisfy a holonomic recurrence. The harmonic numbers and the Catalan numbers. So these holonomic recurrences occur very frequently in analysis of algorithms. So in the analysis of sorting algorithms, the harmonic numbers play a key role. And in the analysis of data structures, say, the Catalan numbers play a role. So Catalan numbers are, the nth Catalan number is the number of planar binary trees with n internal nodes. Other examples in number theory, Perrin numbers, a priori numbers, Schroeder numbers. So as I said, these holonomic sequences are ubiquitous. They permeate this book by Sedgwick and Flageolet on an analysis of algorithms. And indeed, as I think was pointed out by Manuel Cowers, or claimed by Manuel Cowers, approximately 25% of the sequences on Sloan's online encyclopedia of integer sequences are holonomic. So here's a very general class of sequences, and that generalizes in particular these linear recurrent sequences, and we can ask the positivity problem for a holonomic sequence. So given a holonomic sequence, is it positive? Or all elements non-negative? And again, this can be finitely represented by its recurrence and finitely many initial values. Now, at this point, you may be scratching your head thinking, well, does this make any sense? Because already just for the linear recurrence sequences, you could only solve them up to order 5. So why are you trying to solve a harder problem? And indeed, it seems kind of methodologically we're following kind of the dual Polya, or Polya's evil twin, who might say, so here's the kind of reverso Polya, who said, well, if there's a hard problem that you can't solve, then there's an even harder problem that you definitely can't solve. So, why even consider this problem? But in fact, we really are following the kind of the Polya approach, because, well, let's try and say something about the simplest possible problem that's non-trivial. So I claim that the simplest possible problem that's non-trivial for positivity of these holonomic sequences is at order 2 and degree 1. So by this I mean order 2, un is a combination of the two previous terms. And degree 1, these coefficients of the recurrence, bn and an, are rational functions, which are quotients of degree 1 polynomials. So the point here is that if an and bn were constants, then this would just be a linear recurrence of order 2, and we'd know how to decide positivity. And if we had an order 1 sequence, well, then it's kind of easy just by yourself to figure out for an order 1 holonomic sequence, which is so-called hypergeometric sequence, whether or not that's positive. So kind of let's analyze this simplest possible non-trivial case in the spirit of Polya, and we'll find some kind of quite pretty phenomena. So in particular, there is a following notion. There is, given the recurrence, there is a magical number, the so-called critical ratio, which is defined purely in terms of the recurrence and which allows to decide positivity. So what the critical ratio is this a real number? And this number is gotten from the coefficients of the recurrence, and you put them inside a continued fraction. So I have a continued fraction on the right, and the numbers that appear inside the continued fraction are the coefficients of the recurrence. And when this continued fraction converges, it converges to a number, and you call that the critical ratio. And this K notation is this compact Kettenbruch notation for a continued fraction. And this characterizes positivity in the following sense, at least in this order 2 degree 1 case. So modulo some technical assumptions on the signs that we can, that are without loss of generality. The sequence is positive. So the sequence here, starting with initial index -1, this sequence is positive if and only if this critical ratio exists, so the continued fraction converges, and the ratio of initial terms of my sequence is greater or equal to this magical number rho. So if I'm greater than rho, then I'm positive, or greater or equal to rho, then I'm positive. And if I'm less than rho, then I'm not positive. And so if you give me a sequence, I can use this to decide positivity in the following way. I compute this critical ratio to as much precision as I want, and I compare it to the ratio of the first two terms of my sequence. And I ask, well, is one greater than the other? And I can't go wrong, except to extract from this a decision procedure to check whether the sequence is positive. I need to be able to tell whether the ratio of the first two terms of my given sequence is in fact equal to this magical ratio. If it's greater, I can check. If it's less, I can check. I need to know whether it's equal. So this leads to the question, what kind of numbers can appear as these critical ratios? What kind of numbers am I trying to check equality to? So here's a linear recurrence. UN is 3. Here's a linear recurrence with fixed coefficients. And we can compute the critical ratio for this recurrence. And we get it by the continued fraction. And it so happens that this is a relatively sensible number. This is an algebraic number, 3 minus root 5 over 2. So not so mysterious. But here's another recurrent sequence with a slightly more complicated polynomial recurrence. And in this case, the critical ratio is a much more mysterious number. It is 5 minus 6 over zeta of 3. So zeta here is the Riemann zeta function applied at 3. And as was proven by Apery, this number is irrational, but otherwise it's a mysterious number. So it's not known whether this is transcendental or algebraic. So how are we going to compare whether a specific rational number is equal to this? So just wrapping up, we can make some progress here. So what we need to solve is a full abstraction problem. So we need to solve the problem full abstraction for PCF. So PCF here is a polynomial continued fraction because this critical ratio is given by a polynomial continued fraction. So continued fraction where the entries are polynomials, instantiations of polynomials at successive integer values. And the full abstraction problem is, can we decide equality of a PCF with a rational number? Because if we can do that, then we can decide positivity of these polynomial sequences at order 2. And the full abstraction result is as follows. The critical ratio of an order 2 degree 1 polynomial recurrence can be written as the quotient of contiguous values of either the hypergeometric function or confluent hypergeometric function. So the hypergeometric function is a kind of special function. It's a function that goes back to Euler and Gauss. So I don't want to go into the details of what this function is, but this function is given by the following integral formula. So it's given as an integral with these parameters a, b, and c, and z is the argument of the function. And the claim is that if I have a recurrence and I have the critical ratio, it's this real number, this can be written as the quotient of two values of such a function evaluated at an algebraic number. So what? Well, here's the key payoff for this is that linear relations between values of hypergeometric functions, this is a major topic in number theory, going all the way back to the 1930s up to the present day. And you can use results on whether there are linear relationships between values of these functions, these functions evaluated at certain points, to decide equality between a PCF, polynomial continued fraction, and a rational number. So we can implement our PCF equality oracle and thereby decide positivity of these recurrent sequences. So let me now kind of wrap up and take some perspective. So what did we do? So we started seemingly a long time ago by highlighting an open decision problem that was at the core of a very practically successful methodology for proving program termination, namely the decision problem for linear constraint loops. So we showed decidability of this problem for deterministic updates where the variables range over, the loop variables range over the integers. And this solution combined, let's say, techniques from the geometry of numbers and decision procedures for the reals. We didn't make connections with ranking functions. So ranking functions were used for motivation, but in trying to decide termination, we didn't use ranking functions, although connections with ranking functions and what we've done is something that we'd like to look at. in the process, we came to look at initialized versions of the termination problem, where you're given initial values of the variables. And we saw that these were connected with the positivity problems of recurrent sequences, including linear recurrent sequences and holonomic sequences. And these problems are essentially number theoretic in nature, and these look very hard. And to attack these problems, seemingly you can get results only in low order cases, i.e. for loops with 2 or 3 variables. So as I said, not industrial strength. And you need to attack these, you need tools from transcendence theory, number theory, so linear forms in logarithms like Baker's theorem and linear forms in hypergeometric functions. So just to my very last slide, I'd like to talk about the art of the not always impossible. So the kind of spirit of a lot of the work in the POPL community and the work in this CACM article that I was quoting from is, well, this is a hard problem, but it's not always impossible. And here, here's what we can do to approach the problem, and this is going to work in lots of cases. So the spirit of this talk is a little bit, well, this is all very well. It works in practice, but does it work in theory? Can you handle all cases with 6 variables? But let me go back, in fact, to the kind of the spirit of trying to solve problems as generally as possible. So these positivity problems for holonomic sequences seem hard, but in fact, equality problems for holonomic sequences, there's a very well-developed algorithmic theory. So there's this book, A equals B, this very well-known book. And this book is about proving equalities between holonomic sequences. So prove that one sequence is equal to another. And one of the authors of the book is depicted on the right. This is Doron Zalberger, the mathematician. And the equation that's on his t-shirt is in fact an equality between 2 holonomic sequences. And this is something that you can prove using the algorithms that are described in this book. Now, what Zalberger has said is that inequalities are deep whilst equalities are shallow. So it's much harder to prove, for instance, positivity of a holonomic sequence than prove that 2 holonomic sequences are equal. And well, this is, as we have seen in this talk. But nevertheless, this is of course, if you are trying to solve problems in every case, then you need all these tools from number theory and whatnot. But if one is looking to solve problems in some cases, or essentially to prove that this problem is not always impossible, then I think this is a very interesting challenge. And this is a kind of challenge where practical methods for proving positivity, where the kind of abstractions and heuristics that are used for proving loop termination and loop non-termination may play a role. Okay, so this concludes my talk, and thank you very much for your attention.
Thank you very much. That was an excellent talk. So let me start over with the questions that were asked earlier, and this gives everyone a chance to keep posting questions into the chat while I get to them. So the first question is by Adam. He's asking, with most real systems using fixed precision integers, that is modular arithmetic with fixed moduli, what can we learn from results about infinite domains like the integers to enable useful analysis for deployed systems?
Well, so I think it may be the case that so I guess the sense of the question is, well, all systems are finite state in reality, but nevertheless, the way to kind of combat the state explosion problem is to deal with symbolic methods. And so the kind of symbolic methods that enable you to handle, all real numbers or all rational numbers may, enable you to avoid the kind of state explosion problem that happens when you, even in the discrete case. So, I mean, intuitively, you think the discrete case is, in principle, it's easier than the continuous case, but often the continuous case is somehow easier. So dealing with an abstraction is sometimes easier, even if kind of prima facie it seems like it's harder because the system is no longer finite state. So I mean, I can't actually cite particular examples, but I'm saying this as a general principle. But for instance, if you think of using mean field theory in model checking, this would be a kind of something in that spirit.
Okay, the second question that appeared during the talk was there was a statement about the difference between the powers of 3 and 7 being less than a particular value m for finitely many x's and y's, the powers. And someone was asking whether there is any elementary proof for this statement.
Not that I know. So I kind of suspect not. I'm not, I'm not a number theorist, but I got this from a book, and the book seems to suggest not. So I think you need machinery for this.
Okay. So I'm thinking, Michael, should I ask your question or it has been passed?
No, don't worry about it.
Yeah. So I'm not seeing new questions coming in from the audience. So at this point, please post your questions, and also feel free to maybe raise your hand and ask your question live. Okay, so thank you very much, Ben, for an excellent talk. For the first half of it, you made me believe that I can actually do this. Once it got to holonomic numbers, I kind of decided to throw in the towel completely. So because we would have on Clouder the option of having a breakout room and having a quick discussions, we are going to just hang around here. If people are a little bit shy to ask to kind of come forward, and I invite everyone else to move on to the next entry on the program.